All right, today we're going to decode the language of some of the most fundamental building blocks in all of organic chemistry. You know, when you see the intense, bright flame of a welding torch, this is a tool that can literally slice right through solid steel. But have you ever stopped to wonder, what is that fuel? What in the world is burning in there that can get that hot? Okay, or how about something a little more down to earth? Think about agriculture and the simple everyday process of fruit ripening.
So what's the secret? What's the invisible chemical at work that helps speed that whole process up? It's a trick the entire industry relies on.
All right, let's get into it. The answer to both of those questions, the welding torch and the fruit, actually lies with a special group of molecules called unsaturated hydrocarbons. So what are these? Well, they're pretty simple, really. They're just made of carbon and hydrogen. But here's the kicker. They have at least one double or even a triple bond between their carbon atoms. And that little detail, that unsaturation, is what gives them their chemical superpowers. And this brings us to our two main characters for today. First up, we have alkenes, that's said alkenes. And then we have alkynes, pronounced alkynes. So, what's the difference? It's actually super simple, but it changes everything. Alkenes, the alkenes, they have at least one carbon-carbon double bond, and their names always end in -ene. The alkynes, the alkynes, they have a triple bond, and their names end in -ine, double versus triple. That's the whole game. And bam! Just like that, the mysteries we started with are solved. That chemical that ripens fruit, it's ethene and alkene. And the fuel in that super hot welding torch, that's ethine and alkyne. How cool is that? Two really simple molecules doing these incredibly powerful and very different jobs. Okay, so how on earth do chemists come up with names like ethene and ethine? You can actually think of it like learning a new language. Once you get the grammar down, you can basically read and write any molecular structure you see. Thankfully, there's a system. The International Union of Pure and Applied Chemistry, we just call it IUPAC for short, gives us these 4 really clear steps. It's basically this. Find the longest carbon chain that has the double or triple bond, number it so that bond gets the lowest number possible, and then just name anything that's branching off. All right, let's put it to the test. Let's try naming this molecule right here. I know, at first glance, it might just look like a big jumble of letters and numbers, but really, all we have to do is follow those 4 steps. Okay, let's break this down together. Step 1, find the longest chain that includes that triple bond. If you count them up, there are 7 carbons, so our root name is hept. Step 2, what kind of bond is it? It's a triple bond, so that means it's an alkyne, and we add the ending -ine. Step 3, numbering. We want to give that triple bond the lowest possible number, so if we start from the left, it begins on carbon number 3. And finally, step 4, what about the branches? Well, we've got an ethyl group hanging off of carbon number 5. So you put all those pieces together, and what do you get? 5-ethyl-hept-3-ine. See how that works? Every single part of that name is like a precise instruction. It's basically a perfect blueprint for building that exact molecule. Okay, now that we've got the naming down, let's talk about a really fascinating twist in the story. And this is a special feature that only applies to our double-bonded friends, the alkenes. So here's the thing you have to know. A single bond between carbons is like an axle. It can spin around freely. But a double bond, it's rigid. It's locked in place. You can't rotate it. And that has huge consequences for the molecule's 3-dimensional shape. Because of that locked-in-place bond, you can actually end up with 2 totally different molecules that have the exact same chemical formula. We call them stereoisomers. If the important groups are on the same side of that double bond, we call it the cis version. If they're on opposite sides, we call it the trans version. Here's a super simple way to keep that straight. Cis sounds like sisters, and sisters are side by side. Trans literally means across. Think transatlantic, across the Atlantic. So why do we even care about all this stuff? Double bonds, triple bonds, these cis and trans shapes, why does it matter? Well, it matters because this structure dictates everything about how these molecules are going to act and react. You see, those double and triple bonds are just packed with energy. They're basically reactive hotspots. And what they love to do is something called an addition reaction. It's like the bond just pops open, allowing new atoms to come in and attach right onto the carbon chain. Now that's pretty straightforward if you're adding, say, 2 hydrogen atoms. They're identical.
But what happens when you're adding two different atoms, like a hydrogen and a bromine? Where do they go? Does one carbon get to pick first?
Well, it turns out chemistry isn't just random chaos. There's a rule for that. A brilliant chemist named Vladimir Markovnikov figured out a really simple principle to predict what's going to happen. And yeah, you guessed it, it's named right after him. And the rule gets boiled down to this awesome, memorable catchphrase: the rich get richer. Think of it like this: the carbon atom that already has more hydrogens, well, it gets to have another one. The rich get richer.
So after all this, why should you care about this chemical language? Because when you understand how to name these molecules, how to picture their shape, and how to predict their reactions, that's not just chemistry homework. That's the key. It's the absolute foundation that lets scientists build everything from new medicines that save lives to futuristic materials we can't even imagine yet. So the real question isn't just what can we build with this knowledge, it's what are we going to build next?